Hi, and welcome to the Advanced Engineering course. During today's lesson, I'm going to make an overview of software optimization for ARM Cortex A9 and ARM Cortex A53. Both of these processors are part of processing systems for Xilinx Zynq 7000 and Xilinx Zynq Ultrascale Plus. I will start the lesson from explanation of what is a structure of a processing system for Zynq 7000 and Zynq Ultrascale Plus. Also, I will show you what kind of resources enable us to apply optimization for our software. Then I will explain you how to write efficient and optimized code before you will apply any kind of optimization. And finally, I will show you what is hardware and software acceleration. Also, for today's lesson, I create an application where I implement 2D filtering. So here I have implementation of 2D filters with different kind of optimization, which I'm going to explain you during the lesson. I will run the application on Zynq Ultrascale Plus. It's a CG family with 2 cores ARM Cortex A53. The application allows us to estimate how fast our optimization is. So here you can see a processing system, structure of processing system for Zynq 7000 and Zynq Ultrascale Plus. I would like to pay attention on structure of Cortex A9 and structure of Cortex A53. So there are main 2 resources that enable us to apply any kind of optimization. First resources is hardware extension of every CPU in application processing unit, so-called neon or float point unit. As you can see, this kind of extension you can find for every CPU, so it's the same for Cortex A53 and it's the same for Cortex A9. Another kind of resources that allow us to apply any kind of optimization, it's of course memory. For any Cortex, memory has different levels. First of all, it's a level of cache L1 memory, usually it's a 32 kilobytes cache. Then it's a shared memory for all CPUs, it's a L2 cache. For Cortex A9 it's 500 kilobytes and for Cortex A53 it's 1 megabyte. And finally it's external memory like DDR memory, for example, or QDSPI, NAND and NOR. Based on understanding this kind of resources, we can apply 2 kinds of main optimization. First, it's hardware acceleration. Hardware acceleration by using hardware extension of every CPU in our processing system. Second kind of optimization is software acceleration or parallel programming, where we create different parallel threads that can be executed separately by every CPU by using shared memory or common memory for every CPU. Before applying any kind of optimization, we should write optimized efficient code. Writing optimized efficient code is based on memory access and memory hierarchy in ARM Cortex. So, how CPU works? Usually it will look for data in level 1 cache, and if CPU cannot find data in level 1 cache, it will ask level 2, then level 3 or external memory. And as you can see from this picture, time of access for different kind of memory are quite different. For L1 cache it's just 1-2 cycles, for L2 cache it's up to 32 cycles, and very slow external memory 300 cycles. And of course size is very different, so slow memory but biggest size. Okay, let me demonstrate how it works. For demonstration, I implement two functions. It's a 2D filter where I access output array in row and column measure order. So just let's run on our Zynq Ultrascale Plus. Okay, again. So what I have here? Here I create image with a size of 2000 on 2000 elements, and I write to the and I run to the filtering function for row and column measure order. As we can see from the log of our application, row measure order works significantly faster, in 2 times faster than column measure order. So again, why so? For row measure order, all data are placed very close to each other, so it can be placed into level 1 or level 2 cache and can be accessible significantly fast when we compare to access in column measure order, when data placed very far from each other. So in this case, CPU needs to access not level 2 or level 1, but level 3 cache. That make execution of the program significantly slower compared to row measure order. Since we already have optimized efficient code, we can apply further different kind of optimization. And first optimization I'm going to explain, it's a hardware acceleration. Hardware acceleration is applied by using hardware extension of the Cortex ARM processor. So just pay attention on application unit structure, and as you can see, every CPU core has a neon or float point unit hardware extension. Again, every of these CPU cores. So actually, what is this? In hardware, it's implemented like set of registers, and every register has long 128 bits. So it's kind of vectors, and we can place in this vector different elements. The size of elements can be varied, started from 8 bits and up to 64 bits. Then, when we load all these registers, we can apply arithmetic operation, and arithmetic operation should be the same for all elements in vector, and we can have output in our designation register. So this operation is so-called SIMD, or vectorization with neon, single instruction, when single instruction applied to multiply data. Usually for describing vectors and their elements, I use neon data types that are implemented in C extension. It's neon intrinsics in C or C++ languages. So every of these data type can describe a set of these vectors, and of course there are different kind of arithmetic operations that can be applied to this data type. For example, here you can find RGB deinterleaving function when we have input image with red, green and blue colors, and we want to separate all these colors in separate arrays. So straightforward code will look like this. So we just have access to our input array, and then we just read to corresponding output array, red, green or blue color. In neon, it will be implemented like this. So first of all, we need to load input image in our vector, and then we will store from vector to the memory. So in this case, we will use significantly less, in 16 times less operation than we we have when we are using RGB deinterleaving without neon extension. So let's check how this kind of optimization or vectorization can allow us to accelerate our software. Okay, here I have implementation of 2D filtering by using neon, and I just will run this function. Okay, here, and it's third mode. Okay, let's run again. Okay, here we are. So we can see that neon acceleration or hardware acceleration allow us to accelerate our software in 2 times, more than in 2 times, compared to classic raw major order implementation. Let's run again. Okay, and again. So as you can see, it's the same. And a final kind of optimization, it's a software acceleration. Software acceleration is based on memory parallel systems. So memory in ARM Cortex A9 or A53 family can be just like a shared memory when all CPU can access to the same memory, or distributed memory when every of CPUs has his own memory. Based on these two parallel systems, different C libraries for parallel programming are used. For shared memory, it's widespread to use POSIX threads or OpenMP. For distributed memory, usually is used the message passing interface. For shared memory parallel system, we just create a lot of threads, number of threads that are running in parallel. For distributed memory parallel system, we create several processes that are running the same in the parallel. So choice of the tool or library will depend on your application. You can just do research and find more convenient tool for your purposes. Basically, POSIX threads and the message passing interface a little bit complicated, because in this case you have to write a lot of codes to make parallel programming. OpenMP is much easier, because in this case you don't need to write any code, you just need to put into your code different directives that will point what kind of code you are going to run in multi-threading. For example, you can put just 2 lines of code, and for processor it will be comment that you want to create different threads, several threads for your for loop. So the basic idea is the same. By using POSIX or OpenMP, our process will create different threads that are executed in parallel by using our multi-core system. Okay, for demonstration how multi-threading can speed up our application, I will run 2 functions. Okay, I have here, it's one function, it's a parallel threading, and it's a parallel threading plus neon or hardware acceleration. Okay, first let's run for parallel threading. Okay, as we can see, parallel threading. Let's run one more time. So, as we can see, parallel threading allow us to accelerate our software the same in 2 times, like Neon, compared to classic raw major order 2D filtering implementation. By the way, I'm running right now my application on Zynq Ultrascale Plus CG family, which consists only 2 cores. But if you run your application on another family that consists 4 cores, of course, multi-threading, software optimization, acceleration will be significantly or a little bit faster than for system with 2 cores. And finally, of course, since every CPU core consists its own hardware extension and memory, we can apply both software and hardware acceleration. Let's do it and let's measure how fast in this case our application is. So just okay. Okay, great. Again. Okay, great. So here I am checking my output arrays, and I see that any of this function usually works right. So applying hardware and software acceleration allow us to accelerate our software compared to multi-threading, hardware acceleration, and of course a classic implementation of 2D filtering functions. And again, if we run our code on 4 cores Zynq Ultrascale Plus processing system, this number will be less, and maybe we can accelerate our application not in 3, but for example in 4 or even though in 5 times. So finally, let me make a summary of the lesson. So during today's lesson, we considered structure of the processing system for Zynq 7000 Zynq Ultrascale Plus, where I explained to you 2 main resources that enable us to apply any kind of optimization. It's a memory and hardware extension like Neon or float point unit. Memory and hardware extension allow us to apply hardware acceleration and software acceleration. Before we will apply any kind of optimization, we should write optimized efficient code. Writing optimized and efficient code is based on memory hierarchy and speed access. Here I showed you how to compute, how function involve array in row major and column major order, and as you can see that access in row major order significantly faster than for access in column major order. Then I explained to you what is hardware acceleration, what is a hardware extension for every CPU core. It's a set of hardware implemented registers or vectors where we can store and load our elements and apply the same arithmetic operation. It's so-called vectorization or single instruction or multiply data. And finally, I explained to you what is software acceleration, what is a memory parallel system. I showed you different libraries for parallel programming, and I explained to you very short how actually it works. So, and all this stuff, hardware, software optimization, and the writing optimized code, we run on Zynq Ultrascale Plus. It's a CG family with 2 cores, and as we see from our output, that column major order allow us to speed up our application in 2 times compared to column major order. Neon acceleration or hardware acceleration allow us to speed up our application in 2 times compared to row major order. Multithreading is the same 2 times, and of course we can combine near-on or hardware acceleration, hardware and software acceleration. And finally we speed up our application in 3 times. So I hope the lesson is very interesting. So if you have any question, just feel free to email, to write your comments. So thank you for your attention. Bye bye.